Gonzales and Woods. Oh, the main goal of the restoration technique is to improve an image in some predefined sense. So we can say that the restoration tries to recover an image that has been degraded by some prior knowledge of degradation phenomena. So and also we can say that the restoration techniques and enhancement techniques, they have some overlap part with each other. And also, for example, we can say that the enhancement techniques, they are related to the visual human system, and I mean that we can see with our eyes, and can say that this one is related. We can just solve it with the enhancement techniques. For example, contrast stretching considered as an enhancement techniques, and because it is based on the aspect of the human visual system. But removal of noise or removal of the image blurring by applying the de-blurring function is considered as a restoration technique. Now I want to talk about the model of degradation and restoration process. In this slide, I will talk about the restoration. So this one is a model of if the fx and y is the input image, that's a degradation function. For example, like h. We can add also the noise. As a beta x and y. This after this with the h. So something that we have is called as a gxy, that this one is a degraded image. And then we have the restoration. Filters. Here. And the result will be as a x and y. So this part we call it as a restoration. And this part is a correlation. And the more we know about the h and the eta here, the closer we can have this one, the f hat of the xy closer to our input image. Okay. Just remember this one and the model of the image degradation and the restoration. H that we have here, if H was the linear position invariant process, and we have the G, X, and Y equal to the conclusion of the F, X, and Y plus noise here, and also in the frequency domain, we have this one is the convolution, and we have the X, the Y, U, and V. This one is in the frequency domain, and this one is the spectral domain. For the following of my part, we just assume that our H Y is a constant, so we just try to remove. We can deal with the noise. So we just say we don't have this part, and we are just trying to remove the noise from this one, and just try to have the FX here as an output. The main source of the noise is in the digital images. It's just arises during the acquisition of the getting the image, or maybe in the transmission, or also maybe in the acquisition, and another thing is when we are in the frequency domain, when the Fourier spectrum of the noise is constant, so the noise usually called as a white noise. And okay, now let's go to some important noise property, denoising function, and we can just talk about them here. The first noise that I want to talk about is this one, is the Gaussian noise. The PDF of the Gaussian noise just something about that as if. So we call this one as a PDF. Okay, we have the PZ equal to sigma here, and also which this one is the variant. This one is the standard deviation, and also this one, the z bar is the mean of the mean of the z. So the second noise is a Rayleigh noise, and thought this one should be like this. This is A. And the mean of the Rayleigh noise is equal to the A plus B over C, and also the variance of this one is equal to A for this B. And you can see that this density is skewed to the right, and the Rayleigh density can be quite useful for the skewed the histogram. So we call this one as a Rayleigh noise. The next noise is the Erlange or gamma noise, which the PDF of this is this one is a factorial of that. And also we have here this one is C.
And A proper B.
Yes, it's a B. Yes, it's a B. The gamma noise has the two parameters as A and B option. This one is for Z and Z, more than the 0, and for the Z, this one is 0, this one is 0. And A, and if this one has a K, the K is equal to this one. And the mean of the gamma or Lagrange noise is P over, and also the variance is equal to P over square root of A. And the Lagrange and gamma exactly are not same if this one is not this shape, and it has this just gamma function of the B. We call it as a gamma noise, and if it's not, it's the B1, the factor of the B1, we call it as an Erlange noise. The next noise is the exponential noise, which the PD or the exponential noise is there. So you know that this one is there. This one is there. Exponential noise. And the mean is the variance of the exponential noise. And you can see that if here B is equal to 1, the Erlange noise is equal to the exponential noise. next noise is the uniform noise. Zero, otherwise. The mean of the uniform is square of 12. Is one of the famous noise as a salt and pepper or impulse noise. For the A, for the Z equal to A, is a PA. Otherwise, it's 0. And if the B is rather than the A, so the intensity of the B will appear as a large dot in the image, and also the A should be bright. But if PA or PB, one of them is a 0. We call it the impulses as a unipolar noise. And also if the PA is equal to PB and maybe equal to 0, this one is a symbol of the salt and pepper noise. And also, we call it as a bar color also. It has a salt and pepper or noise also. And also it has a warning, also as a filter drop out. Maybe you just see in some papers they use as a S5 noise also. All of these ones refer to the impulse noise with some condition. So, and also if for the salt and pepper, if the we have the negative impulses, we call it as a pepper or as a black, and also if it's positive because as a salt or as a white. The Gaussian noises arises in an image due to the factors such as electronic circuit noise or as a sensor noise due to the poor illumination or high temperature, and we have the noisy image with the Gaussian noise. The Rayleigh density is helpful in the property noise phenomenon in the range imaging. And exponential and gamma densities they are found in application related to the laser imaging. Impulse noise is found in situation where we have the quick transit, such as faulty switching. And uniform density is quite useful as a basis of huge random number generation that are used in the simulation. And with the visual, it's so difficult to differentiate between the first five nodes. I mean the Gaussian, the Rayleigh, the exponential, the gamma. But we can see easily the salt and pepper noise in the images. If we want to call it as this one as a periodic noise, and because they arises typically from the electrical or mechanical interference during the acquisition. And if you want to estimate if we have the estimate of the noise, we can, and if we have the histogram of the noisy image, so we can estimate which noise just apply to this noisy image, and also we can find the parameters that they are using in that image. For example, for example, if we have the noisy image here, and we want to find that when we have the histogram of this one, we first want to just take the sub image of as an S from this image called as S, and also just find this is Z, which this one is the normalized histogram values of we have from the histogram. This is the I, and so we can easily find the Z bar as a norm. If L is all of the intensities that we have in the image, so the Z bar is equal to Z I, and also the variance is equal to Z I. So we can find these two, and also we have the shape of the histogram. And we can easily find the parameters of these two. And if some of the noises they have the A and B parameters, we can find from after finding the mean and variance, we can find A and B. And also for the salt and pepper, we have PA and PB from the histogram, and we can easily find those polarities. As I said that we have the X and Y is equal to Y in the structural domain and also the because we don't know exactly these terms, so we cannot easily just subtract the x by the eta and find the fx or the capital fx, and it's not realistic. So we should find another way to find the image that is similar to the fxy. So now I want to talk briefly about the noise reduction in the spatial filtering. First, I will talk about the mean filters. The first mean filter that I want to talk is the arithmetic mean filter. So if we have the S, as I said, that the S is the sub-image of the noisy image, and this one is the set of the all of the x and y in the all of the x and y in that sub-image. This one amplified as a S, x and y. And the x and y, they are the coordinates of this sub-image. For the arithmetic mean filter, we just find the average value of the corresponding image in the SXY and put in the center of that center of the SXY. So we have the So we just find the arithmetic mean of all of the pixels here and just put it there in the formula. And the arithmetic filters can smooth the local variation in image, and so it can be used for the noise reduction. But this one is one of the simplest noise, or we can say that the simplest noise filter. The second one is the geometric mean filter. Which we have the product of the G and T for all of the S and T. X and Y. Geometric mean filter can smooth more compared to the arithmetic mean filter. But the problem is that this one, if we just use this filter, more data we lost. We can lose more data from using this filter. The next one called as a harmonic filter. harmonic mean filter. And this one is this. The harmonic mean filter is good for the removing the salt and pepper from the noisy image. It's good for the salt noise, but it's not good for the pepper noise. And also, it's good for some other noise like the Gaussian noise. And this one is good for the Gaussian noise also. Another mean filters. What is it? Control harmony. Mean filter. And we call Q as order of the control harmonic mean filter.
Is there any special value for the Q?
Yes, I will talk about this. Yes. And this one is working well for the reducing or visually eliminating of the effects of the salt and pepper noise. This one is good for the salt and pepper noise. And we have something for the condition for the Q. If Q is bigger than the 0, this one can eliminate the pepper noise. And if the Q is less than 0, it's good for the salt noise. So if the order of the control harmonic is bigger than 0, is for pepper noise, and this is less than 0 is for the salt noise. And if Q is equal to 0, you can see that the control harmonic just became the arithmetic noise. So it can do something that the arithmetic noise can do that. And also if the Q is equal to -1, the control harmonic mean filter becomes the harmonic filter. Harmonic mean filter. Okay. These are some of the mean filters, and we have another filters that they are not linear. We call it as order statistics filters, and there are non-linear filters. Based on the ordering of the pixels, and they are related to the place of the position of the pixel in the image or in the sub-image. The first one that we have as order statistics filters that all of you know is the median filter. That median filter is one of the famous order statistics filter. Which one is the best known for the order statistics filter, And for this one, we just replace the value of the pixel by the median of the SX after sorting the pixels. For example, if we have the if our SX is something like that, to the median of the x t for the all of this t x and y. So if this one is x and y, first we should because this filter is related to the ordering of the pixels in the SX. First we should sort all of the pixels density value in this in SX. So we have 0. For the median filter, we have the window size. For example, if we have, for example, this one, we have our window size is 3 by 3. So we just sort first, just sort it, and then find the median of this set, and we put it in the center of this S and SX. And this one is really is so effective and removing noise, while this one is not destroying the edges, and also this one consider less blurring than the linear smoothing filters. And this one is good for both bipolar and unipolar noises. The next one, we have this concept of the max and mean filters. First, I want to talk about the max filter. In the max filter, we can find the f hat x and y. We just find the max of the x and y. For example, in this subpixel, you should find the highest one. So this one is 219. We should put the 219 instead of the 77 in the center here. So as you can see that if we just use the max filter, so we have the result should be so bright, and for the part of the image that they are bright in the noisy image. After applying this max filter, we have more bright pixels in the image. The next one, as you can guess, is the mean filter. And the mean filter is same as the max filter, but instead of the max, we have the mean of the S and T. So, for example, here, instead of the 77, we should put the 0 instead of the 77 in the center of the S and S6. So, this one is exactly the opposite of the max filter, is working at the opposite of the max filter. So, we have more darker pixels in the image after applying these filters. And one of the important things, if we have the face images, we have the images that has the face on this image, and we want to find the eyes in that image, this filter is really good for finding the eyes in the images with the face. The next one is the max min filter. If we use the max min filters, this one can blur the noisy image, and because it's replacing the pixels with the difference of the max and the mean of those pixels in the SX. So, for example, if here is 10, so we have the 209, and we should put this one in the center of this sub image. And one of the most important things about the max min filter is that if our window size is small for the max filter, for example, if our window size is 2 or 3, this max min filter really works for the it's good for the edge for the detector of the edges in the image. The next order static filters is a midpoint filter. And this one is similar to the max min that can blur the image by replacing the average point of the highest and the lowest pixels in the sub image. So for that example, we have we just put the circle on the 7 on the center of that sub image. And this filter really works for the random uniformly distributed noise, the Gaussian, and also the uniform noise. The last one is the alpha trim mid filter. So just suppose that we did just the d over 2 of the highest and the d over 2 of the lowest of the sub-image pixels value, and I mean after the sorting the pixels value, and then for the if we just call it the remaining if we call it the remaining nm minus d as a gr of the x and y. So this filter goes by the averaging of the remaining n minus d pixels, and after that just put it in the center of this subpixel effect. So we have and always the d is between the 0 and n minus 1, and if d is equal to 0, so you can see that the alpha trim mean filter becomes the arithmetic mean filter. For the d equal to 0, and for if we have the d equal to n minus 1, so the alpha trim mean filter becomes the median filter. And the alpha trim mean filter is good for the situation that we have the multiple types of noise, like we have combination of the salt and pepper, the Gaussian noise, and this one is really works for those filters. So for example, for this one, if I have to have the sample, we have 10 here. So and if we find the d equal to 4, so 6, so should have the so we have the we should take 3 of this side and also 3 of this one. So for the average of this one, we have the gain 77, and we should put the 77 that we have here also. We can put it here, and we should just find the average of this remaining pixels value in the center of the subpixel image. Okay, really, today I want to just talk about the introduction and the image restoration and the reconstruction. So this one is around the 30 pages of this chapter book. So next time I will talk about the adaptive filters and for the some good denoising filters in the rest of that, or maybe we can just have also solve some examples of this chapter in this book. Okay. Any question?